Welcome back to Very Ordinary Differential Equations. In this lecture, we learn how to apply the technique of variation of parameters to higher order equations. Now, the technique of variation of parameters actually generalizes pretty well to higher order differential equations. So let's suppose you have a linear differential equations as written here. The complementary equation, we're going to assume we've already determined a fundamental set of solutions given by y1 through yn. The only goal now is to apply variation of parameters to find one particular solution to the non-homogeneous equation. We're going to presume that our particular solution y sub p can be written in the following way: a sum of u1 y1 plus u2 y2 and so forth. The y sub I, that's our fundamental set of solutions to the complementary homogeneous equation, and the u sub I are unknown functions that we're going to determine. So we've presumed that our particular solution y sub p can be written in the following way: unknown functions ui times the yi, which form our fundamental set of solutions to the complementary homogeneous equation. If we take a first derivative of this construction, yp prime, well, through the product rule, we're going to get various terms where we have the ui and the derivative of y's. I'm going to collect all of those: u1 y1 prime, u2 y2 prime, all the way up to un yn prime. The product rule also forces us to take terms u1 prime y1, u2 prime y2, all the way up to un prime yn. We're going to make a simplifying assumption about the function y sub p. Specifically, all the terms where we have the derivative of u times the original function's y, if you add all of those up, you get out 0. We are assuming that this holds. So all of these terms added together, we're assuming add up to 0. Therefore, yp prime can just be given by this sum here, where the u sub I have not had derivatives applied, but the y sub I have. So we've made this simplifying assumption that yp prime is actually just given by u1 y1 prime plus u2 y2 prime and so forth. If I take a second derivative, well then the product rule, again, I'm going to get u1 y1 double prime plus u1 prime y1 prime, and I'm collecting all of the terms where I have one derivative of each term here, but all the terms where the ui are unaffected and the y's have had derivatives taken twice, I'm collecting here. We're going to make another simplifying assumption that all of these add up to 0. Well, if all of these add up to 0, then yp double prime can be given just by these terms here. So we have presumed that our solution has the form we've been using. We assumed that the sum of ui prime times yi was 0, which we reused to derive that yp prime had a particularly nice form. Then we assumed that the sum of ui prime yi prime was 0, which we used to derive that yp double prime had a fairly nice form. We continue to assume that ui prime times higher and higher derivatives of the yi add up to 0, for I going from 0 and 1 up to n minus 2. And again, for I equals 0, that was this assumption that we made here, which we used to derive a nice form for yp prime. For I equals 1, it was the second assumption we made, which we used to derive a nice form for yp double prime. So we keep assuming this, and what we derive is that the next derivative of yp continues to have a fairly nice form. For I equals 0, we got that the first derivative of yp had this nice form. All the way up to, when I is n minus 2, we're going to get that the n minus 1 derivative of yp takes the particularly nice form. So let's just refresh. We assumed our particular solution took this form. Then we assumed that various sums of this form were always equal to 0. But for which index I did we make this assumption? Now, if I is 0, this allowed us to conclude that yp prime was particularly nice. When I was 1, it allowed us to conclude that yp double prime was particularly nice. We want to make enough assumptions so that up to the n minus first derivative of yp are particularly simple. And if we want the n minus first derivative of yp to take a nice form, we need one lower choice of I here. So I goes from 0 up to n minus 2. This allows me to conclude that the I plus first derivative of yp takes this simple form, meaning The derivative of yp takes the simple form for the first derivative through the n minus first derivative. So we've assumed that our solution takes this particular form, that these sums are 0 for index 0 through n minus 2, allowing us to conclude that the derivatives of yp are fairly simple up until the n minus first derivative. We're going to take one more derivative, but we're not going to make a corresponding simplifying assumption about it. Now the product rule spits out the terms that we expect. We end up with one more derivative on the y's, or not getting one more derivative on the y's, but also getting a derivative on the u's. Now we're going to take this nth derivative for yp, all of these lower derivatives for yp, and we're going to put them into the original differential equation, p naught times the nth derivative, p1 times the n minus first derivative, and so forth, all adding up to the forcing function. So here we have the form of the forcing function. Some simplifying assumptions allowed us to conclude that the derivatives of y sub p were fairly simple up until the n minus first derivative. However, the next derivative then takes this form. When we put this into the differential equation, we're going to collect terms according to which u's are multiplying things. So if I plug this in for the nth derivative of yp, u1 will be multiplying the nth derivative of y1, but it will also be multiplying p naught. But in the n minus first derivative, u1 will be multiplying the n minus first derivative of y1, but it will also be multiplying p1. In the n minus 2 derivative, it'll be multiplying the n minus 2 derivative of y1, but it'll also be multiplied by p2 in the differential equation. So if we continue that argument, u1 is multiplying p naught nth derivative of y1, p1 n minus first derivative of y1, p2 n minus 2 derivative of y1, all the way up until when I is equal to 1, we would have u1 times the first derivative of y1 times p sub n minus 1, and back here we would have u1 times y1 being multiplied by pn. So here are all of the terms that have a u1 in them. Similarly, what is u2 being multiplied by? Well, the only difference going from u1 to u2 is that they're all going to be multiplied by y sub 2 and the derivatives of y sub 2. All the way until what's multiplying un? A very similar expression, but involving y sub n rather than y sub 1. The only thing we haven't accounted for is this parenthetical term here that involves derivatives of u1, u2, and so forth. Well, we don't do anything with this. We're not simplifying it or manipulating it, but it only appears in our differential equation once. It only appears in the term for the nth derivative of yp, in other words, being multiplied by p naught. So we have p naught times this parenthetical expression, and now on the right-hand side we just have our forcing function. Now something extremely nice happens, and it was really the point of making all the assumptions we've made earlier. What were the y1, y2, and so forth? They were a fundamental set of solutions to the complementary equation, meaning if you were to take y1 and plug it into the original differential equation, you would get out 0. It solves the complementary homogeneous equation. If you take y2 and you plug it into the original differential equation, you get out 0, and so forth. So this parenthetical term right here is exactly taking y1 and plugging it in to the original differential equation. So this parenthetical term is 0. In fact, all of the parenthetical terms are 0 except for this one here, because these have the u1 prime, u2 prime, and so forth. In other words, once we drop all of these terms and divide by p naught, we get this expression here. This expression here is equal to the forcing function divided by the leading coefficient of the differential equation. So I know it's been a bit, but let's just make sure we're all on the same page. We've presumed our particular solution can be written like this. We made simplifying assumptions that the derivatives of u1, u2, and so forth times y1, y2, and so forth, either the original functions y, the first derivatives up to the n minus second derivatives, that this corresponding sum was always 0. And the utility of making this assumption was that when we took yp, n derivatives, n minus first derivatives, and so forth, and threw it into the original differential equation, we were able to conclude that this expression here, involving the first derivative of u1, u2 up to un, and the n minus first derivative of y1, y2 up to yn, was equal to the forcing function over the leading coefficient. We can write this in matrix form as follows. So let's take a look at how this giant matrix of y1, y2 up to yn, first derivative, second derivative, third derivative, up to n minus first derivative, times this column of derivatives of the ui can be expressed as this column here. So what happens in our first row? We get y1, u1 prime, y2, u2 prime, and so forth. However, that's exactly this expression here for I equals 0. u1, u2 all have one derivative. y1, y2, and so forth don't have any derivatives. y1, u1 prime. So the first row in the resulting column is 0. What about the next row? We would get y1 prime, u1 prime, y2 prime, u2 prime, and so forth, which is exactly this simplifying assumption for I equals 1, so it's also 0. In fact, everything in the result is 0 except the last row. We get y1 n minus 1 derivatives, y2 n minus 1 derivatives times u1 prime, u2 prime, and so forth, which exactly spits out this here. So the last row is the forcing function over the leading coefficient, but everything else is zeros. So here's where we are. We assumed our particular solution was written like this, and with some simplifying assumptions, we have this nice matrix form. Now this matrix is just the Wronskian. The top row are the elements of our fundamental set of solutions, and then row by row we go one derivative, two derivatives, up until we have an n by n matrix, so we take n minus 1 derivatives here. This is the Wronskian matrix of our fundamental set of solutions. By assumption, a fundamental set of solutions must be linearly independent, and therefore this matrix is not 0, it is invertible. So if we abbreviate this as Wronskian times column of derivatives of u is equal to this particular thing on the right, which is all zeros except for this last term. Since the Wronskian matrix is invertible, we can solve that this column of derivatives of u1, u2, and so forth is given by the inverse of the Wronskian times this column f. If we can solve this for this column of derivatives of u1 prime, u2 prime, and so forth, we will be able to anti-differentiate each term in that resulting matrix here and recover the individual ui's. And once we have the ui's recovered, we come back here and plug them in there to get our y sub p. So here we have Wronskian times column of derivatives of the ui is equal to this particular column on the right, which is all 0 except for the last entry. We can solve for the derivatives u1 through the derivative of un by inverting that matrix, but that would be a nightmare. We're not going to try to invert the Wronskian. Okay, not only is it presumably a large matrix, it's not even a matrix of constants, it's a matrix of functions. So instead we're going to rely on Cramer's rule, a method for solving this problem, which interpreted for this particular setup would say the following. uj prime is given by -1 to the n minus j times the forcing function times w sub j over the Wronskian times the forcing function p naught. So w is the determinant of the Wronskian, and w sub j is the determinant of the n minus 1 by n minus 1 matrix formed by removing the jth function from the expression. So for example, w sub 1 says forget y sub 1. So remove this column, and then I don't need the last row either in order to make the correct size matrix. So always remove the last row, and then remove one column according to what the index j is. And w sub j is the determinant of that sub-matrix. So here's our expression. Having assumed that the y1 through yn were a fundamental set of solutions, and the solution yp was u1 y1 plus u2 y2 all the way up to un yn, we were able to finally say that the derivative of uj is given by this expression. Wj is the determinant of a submatrix formed by striking out the jth column and always striking out the last row, and W is the determinant of this Wronskian matrix. Once you have found all of these derivatives, you anti-differentiate them to recover U sub j, and then you are done. So given the original differential equation, let's just refresh what are the steps to solve using variation of parameters. Suppose you have a fundamental set of solutions y1 through yn. You want to make one particular solution u1, y1 plus etc. up to un, yn. So you build a matrix of the fundamental set and derivatives through the n minus first derivative. You build up that Wronskian. You compute the determinant of the Wronskian and the determinants of the appropriate submatrices. Then you solve each of uj prime is -1 to the n minus j times this expression. Notice the only thing that changes as you change the index j is this alternates between plus or minus 1, and this numerator gets a wj. Otherwise, the forcing function over the determinant of the Wronskian times p naught is actually the same in every expression. So you get all these uj primes, you anti-differentiate each of them, and then you have your particular solution. Now this sounds like a lot. It's very intimidating at first. However, once you get the hang of it, it's actually quite mechanical and just a nice flow to go through. So let's try an example. Use variation of parameters to find one particular solution to this differential equation, given a particular fundamental set of solutions to the complementary equation. So to match all the notation that we used in our initial discussion, we have p naught is the leading coefficient of the differential equation, that's 2. The forcing function is 6e to the 4x. y1 is e to the x, y2 is e to the 3x, y3 is e to the minus x over 2. I can put them in any order I want, but I may as well just use the order they were written in. So we set up this Wronskian matrix. First row, y1, y2, y3. Second row, derivative. Derivative of e to the x is e to the x. Derivative of e to the 3x is 3e to the 3x. Derivative of e to the minus x over 2 is -1/2 e to the minus x over 2. Next row, take a derivative again. Now I have a 3 by 3 matrix, I'm done. So I take a determinant of this. Okay, I'm just going to expand along the bottom row. Why am I expanding along the bottom row? Well, let's keep track of plus versus minus 1. Okay, so this, you always start with a plus 1 in the upper left. This would be minus 1, so down here is a plus 1 again. So I extract e to the x times the 2 by 2 matrix formed by striking out that row and column. Well, remember, the wi's were always formed by striking out the last row and then a particular column. So if I expand the determinant of w by going along the bottom row, I will always end up generating w1 and then w2 and then w3 and so forth. So because we started with a plus 1 here, we have plus e to the x times w1 minus 9e to the 3x times w2 plus a quarter e to the minus x over 2 times w3. Point being, once I compute w1, w2, and w3, expanding along the bottom row gives me a quick way to compute w without having to construct this larger matrix and find its determinant all over again. So we're actually just going to compute these smaller determinants and then use this expansion to get the determinant w altogether. All right, so w1 is the determinant of the matrix formed by striking out the first row and last column, leaving behind these 4 entries here. So there's w1. w2 is the matrix formed by striking out the last row and the second column, leaving behind these 2 e to the x's and then these 2 entries. So we make that matrix. w3 is the matrix by striking out the last row and the last column, leaving just these 4 entries, e to the x's on the left and various e to the 3x's on the right. So we just have to take determinants of these smaller matrices. That will give me w1, w2, w3. I take those values back here. That will give me the value of w, and then we're basically done. So here was w1. We take its determinant. It works out to be -7/2 e to the 5x over 2. w2 was this matrix, and its determinant is -3/2 e to the x over 2. W3 was this matrix here, and its determinant is 2e to the 4x. As 2 by 2 matrices, these weren't so bad to compute determinants of. What about the overall Wronskian determinant W? Well, we had this expression that we got by expanding the last row, but we've already computed W1, W2, W3, so throw those in. W1, W2, W3 added in. Now I just have to take these various products and compute the resulting sum, and it's not so bad. It's just 21/2 e to the 7x over 2. So given this fundamental set of solutions, we constructed a 3 by 3 matrix. For certain 2 by 2 matrices, we computed determinants. We then used those determinants to compute the determinant of the overall 3 by 3 matrix. While it's a bit of work, we haven't had to do anything clever. Once we have the fundamental set of solutions, we construct a matrix, we pull out some submatrices, we do a bunch of computation. Now we can start computing the ui primes. u1 prime, -1 to the n minus 1, since we have a third order equation, this is n. So we have -1 to the 3 minus 1, w1 forcing function over w leading coefficient. The forcing function is always going to be 6e to the 4x. W was just this expression here, times the leading coefficient, which is 2. So notice when you multiply that 2, it exactly cancels this denominator. So W1, -7/2 e to the 5x over 2, times f, 6e to the 4x, results in -21 e to the 13x over 2. W, 21/2 e to the 7x over 2, times leading coefficient 2, results in 21 e to the 7x over 2. The 21s cancel, the exponent simplifies, and this is just -e to the 3x. So u1 prime is just -e to the 3x. So can we recover u1 from this? Absolutely. Anti-differentiate. We're not looking for any possible antiderivative. All we need is some antiderivative, so you're free to pick the constant of integration to be anything you want. So let's pick the constant of integration to be 0. So anti-differentiating -e to the 3x, u1 is -1/3 e to the 3x, plus any constant, but 0 is an easy one. And with this as our choice for u1, and y1 was just e to the x, u1 y1 is -1/3 e to the 4x. Now we just have to do that again for u2 prime and u3 prime. All right, so here were our w, w1, w2, w3. u2 prime is going to be given by -1 to the 3 minus 2 w2f over wp0. wp0 is going to be the same in every expression, 21e to the 7x over 2. w2 we computed here. Multiply by the forcing function. We'll simplify to this. And we just have 3 over 7 times e to the x, and that's u2 prime. Well, find any possible antiderivative, like 3/7 e to the x plus 0. There's a nice choice for u2. Multiply this by y sub 2, which was e to the 3x, and get 3/7 e to the 4x. And finally, u3 prime is -1 to the 3 minus 3 w3, forcing function wp0 all the same that they have been. w3 was 2e to the 4x. Our forcing function is 6e to the 4x. Their product in the numerator will now be 12e to the 8x. All right, this simplifies to 4/7 e to the 9x over 2. We just need one possible antiderivative, so take the constant of integration to be 0. u3 is 8/63 e to the 9x over 2, and therefore u3 times y3 is 8 over 63 times e to the 4x. Okay, so we're finally ready to be done. Having assumed yp was given by u1, y1, u2, y2, u3, y3, we went through a bunch of work and we solved for what's u1, y1, what's u2, y2, what's u3, y3. From the previous slides, here they were, -1/3 e to the 4x, +3/7 e to the 4x, and 8/63 e to the 4x, for a final result of 2/9 e to the 4x. I will point out, undetermined coefficients is actually quite easy for this problem. We have a bunch of constant coefficients here, and the forcing function is just something times e to the 4x. E to the 4x is not a solution to the complementary homogeneous equation. So if I had simply assumed that y sub p was an unknown coefficient times e to the 4x and thrown it into the differential equation, we would have quickly determined that the unknown coefficient is 2/9. The purpose of this example was not variation of parameters is the easiest way to do it. The purpose of this problem was to work through variation of parameters when none of the particular computations were that bad. So for a second example, let's change things up. Use variation of parameters to find one solution to this differential equation, already knowing that x cubed, x to the fifth, x to the seventh form a fundamental set of solutions to the complementary homogeneous equation. So we make our matrix by taking the top row to be our fundamental set, one derivative, two derivatives. Okay, once you have a square matrix, you're done. If I expand this along the bottom row, we get 6x times the determinant of this matrix, and that's W1, minus 20x cubed times the determinant of this matrix with these two entries and these two, and that's W2, plus 42x to the fifth times the determinant of this matrix here, this 2 by 2, and that's W3. So W1 is this 2 by 2 matrix, and its determinant is pretty easy to compute. It's 2x to the 11th. W2 and W3 correspondingly, not too bad. Quick determinants to compute. The fact that our fundamental set was just powers of x makes this quicker than the last problem. So here are the determinants W1, W2, and W3. W, the overall determinant, we already expanded along the last row. We've already found W1, W2, and W3. So we can quickly compute W itself to simply be 16x to the 12th. W times the leading coefficient is always the denominator in the next part of the problem that we work through, so we're just going to go ahead and state that W, 16x to the 12th, times the leading coefficient of the differential equation, which is x cubed, up here, this x cubed. So that denominator is always going to be 16x to the 15th. All right, so we've computed W1 to be 2x to the 11th and WP0 to be 16x to the 15th. We are now in a position to compute U1 prime. Negative 1 to the 3 minus 1. This 3 is the order of the differential equation, third order differential equation. Our numerator is W1 times the forcing function, so 2x to the 11th times x to the 12th. WP0 we already computed before. This simplifies down to 1/8 x to the 8th, and that's U1 prime. So take any antiderivative you want. So let's use a constant of integration, which is 0. So U1 is 1/72 x to the 9th. Multiply it by Y1, the first element of our fundamental set of solutions. So multiply this by x cubed. For U1, Y1 is 1/72 times x to the 12th. Similarly, W2 we already computed to be 4x to the 9th. So U2 prime simplifies down to negative 1/4 x to the 6th. Negative 1 to the 3 minus 2, so that's a negative 1. W2f, so we have 4x to the 9th times x to the 12th. And WP0 we already computed before. So this simplifies down to negative 1/4 x to the 6th, and that's U2 prime. Take any antiderivative you want, like negative 1/28 x to the 7th for U2. Multiply by Y2, the second element of our fundamental set, so multiply it by x to the 5th, and end up with negative 1/28 x to the 12th. And finally, W3 is 2x to the 7th, WP0 we already computed. Therefore, U3 prime, given by the same formula, it all simplifies down to 1/8 x to the 4th. That's U3 prime, so to find U3, we anti-differentiate and use any constant of integration we want, like 0. So U3 is going to be 1/40th x to the 5th. Multiply by Y3, the third element of our fundamental set. Multiply this by x to the 7th, get 1/40th x to the 12th. So finally, we can say Yp is U1y1 plus U2y2 plus U3y3. We already computed each of those. It simplifies to 1/315 x to the 12th. So in the end, Yp is just a constant times x to the 12th. You may ask, why did we not just use the method of undetermined coefficients? There's two reasons, one a small reason and one a very big reason. The small reason is that our forcing function is a polynomial of degree 12. Meaning, if we were to use the method of undetermined coefficients, Yp would have been an unknown polynomial of degree 12. Something times x to the 12th plus something times x to the 11th plus something times x to the 10th, and so forth. There would have been a whole lot of undetermined coefficients to work out. Now that's the small reason. The real reason is that the method of undetermined coefficients works cleanly when your differential equation has constant coefficients. Ours does not. We have x's here. It's not to say that the method of undetermined coefficients can't possibly work, but it really doesn't work as nicely as we've come to expect. Okay, so the method of undetermined coefficients for practical purposes is really restricted to constant coefficient differential equations. Since this differential equation does not have constant coefficients, the method of undetermined coefficients was never really on the table, but variation of parameters worked out pretty nicely. For our last example, find one solution to x times the fourth derivative of y plus 4 times the third derivative of y is 6 log x, where we're given a fundamental set of solutions to the complementary equation. We're going to be going through all the same steps. However, since we have a fourth order equation and 4 elements in our fundamental set of solutions, we're going to have a 4 by 4 matrix to construct for the Wronskian. However, many of the derivatives involved are going to be very simple, which is going to make our lives a bit easier. So here is our Wronskian matrix. We put the fundamental set in the top row, and then row by row we keep computing derivatives. Okay, now notice there are a lot of zeros that appear. When we expand this matrix along its bottom row so that we get W1, W2, W3, and W4 showing up, a lot of zero coefficients are involved. Even though we have some zero coefficients in there, we do ultimately have to compute W1, W2, and W3, as they are involved in finding U1, U2, and U3 later. So let's compute W1. So if you refer back to the matrix of the fundamental set and all of its derivatives, okay, you construct W1. You can also construct W1 directly by saying remove the first element. So remove 1 from our fundamental set, leaving just x squared 1 over x, and construct a 3 by 3 matrix by taking those, their derivatives, and second derivatives. I need to compute a determinant of this. Now this is a 3 by 3. I'm just going to expand along the top row. X times this submatrix minus x squared times this determinant plus 1 over x times this one. Works out like this, simplifies down to just 6 times 1 over x. So there is W1, 6 times x to the minus first power. Now we're going to do W2, so I remove x, the second element from the fundamental set, and I make a 3 by 3 matrix by putting 1 x squared and x to the minus first in the top row, and then taking derivatives. First derivative, second derivative, I've got a square matrix now, I can stop. I'm actually not going to expand this along the top row. What we could have noticed in the last one also is if I expand this along the left column, it's a lot easier. So I get 1 times this 2 by 2 matrix and then some zeros. This works out to just be 6 times x to the minus second power. And there is W2. To compute W3 and W4, it's really all the same work. So for W3, remove x squared, take 1x and x to the minus first, and make a Wronskian-like matrix out of that. Expand this along the left column, and you're going to quickly get that the determinant is 2x to the minus third. For W4, if I remove 1 over x, the last element from the fundamental set, I just have 1x squared. First derivative, second derivative, expand along the left column. Its determinant is just 2. So we've computed W1, W2, W3, W4. So now we can go back and compute the value of W. Remember from way back a couple of slides, it was a bunch of zeros and just negative 6x to the minus fourth times W4. W4 was just 2. So overall, W is just negative 12x to the minus 4 power. WP naught, the leading coefficient, well, the leading coefficient of the differential equation is x. So if I multiply W by x, I get negative 12x to the minus third. Now we can start computing the derivatives, U1 prime, U2 prime, U3 prime, U4 prime. All right, Ui prime is negative 1 to the 4 minus I, WIF over WP naught. So negative 1 to the 4 minus I is going to alternate between plus or minus 1. The forcing function is 6 log x, and WP naught we've computed to be negative 12 x to the minus 3. I'm just going to take this minus sign and increase the power of negative 1. So this becomes negative 1 to the 5 minus I. 6 over 12, I'm just reducing to a half. And this x to the minus 3 in the denominator, I'm bringing up as an x cubed in the numerator. So now we've got a formula. Ui prime is negative 1 to the 5 minus I. We ended up with an extra power of minus 1. X cubed log x wi over 2. So u1 prime, x cubed log x, w1 was 6x to the minus 1 over 2. 6 over 2 gives me 3. X cubed times x to the minus 1 gives me x squared. I can take any antiderivative I want. 1/3 x cubed, 3 log x minus 1. Then I multiply by y1. However, y1 was just the constant 1. So here's u1, y1. It's 1/3 x cubed times 3 log x minus 1. We keep doing similar work. u2 prime is now given as this. w2 was 6x to the minus 2. So u2 prime is just 3x log x. Take any antiderivative you want, like 3/4 x squared times 2 log x minus 1. Multiply by y2. y2 being the second element of our fundamental set, which is x, so it's just going to increase this power here by 1. u2 y2 is 3/4 x cubed times 2 log x minus 1. u3 prime given like this, w3 was 2x to the minus 3. All terms cancel except for the log, so u3 prime is log x. We just have to antidifferentiate log x, and we get x times log x minus 1. Then I have to multiply by y3, the third element of our fundamental set of solutions, which is x squared. Overall, u3 y3 is x cubed times log x minus 1. And finally, u4 prime given as such. w4 was just the constant 2, so u4 prime is x cubed log x. Antidifferentiating this isn't particularly fun, but it will result in something not so bad. 1/16 x to the 4th times 4 log x minus 1. Then I just take u4 y4, y4 being the last element of our fundamental set, or 1 over x, so I'm going to cancel 1 power of this x here. So here's u4 y4, 1/16 x cubed times the quantity 4 log x minus 1. Altogether, we can now construct y sub p as u1 y1 plus u2 y2 plus u3 y3 plus u4 y4. Here are all of the terms we've computed. Factoring out a common x cubed, if you like, here we have y sub p, x cubed times this enormous parenthetical term. We can simplify what is multiplying a log x and what are constant terms, and we end up with x cubed times 15/4 times log x minus 103 over 48. All right, so altogether, what have we got? Variation of parameters is a technique to find a particular solution to a differential equation if you already know the fundamental set of solutions to the complementary equation. Unlike undetermined coefficients or Laplace transforms, variation of parameters is not effectively restricted to constant coefficient equations. Those other techniques can be adjusted to other equations, but they get really ugly. Variation of parameters, however, if you know a fundamental set of solutions to the complementary equation, the coefficients aren't that big of a deal. It's a big if, by the way, to say if you know a fundamental set of solutions. However, it does take a lot of steps. And in the examples we did here, I even glossed over a lot of the time in doing this by hand. There's a lot of integration by parts in all of the examples that we did. And I just said, take any antiderivative you want. Oh, here's one. Actually doing that antidifferentiation can be very time consuming.